All right, good. Thanks. Well, thank you for inviting me to speak here and no, sharing this long overdue paper that I think I talked about I guess the inception maybe 4 years ago. Uh, it's finally out, at least part one. So actually here, it's work with Ben that I've been doing mostly when I was at UMass. And so finally in January this came out. Uh, so well, I mean, you've seen or you've heard and seen the title. So the title, the idea is to prove the weak gravity conjecture in well with some caveats. So in the perturbative string theory, that really will mean a tree level in bosonic string theory. But some of those things we have arguments to say that those are not problems. But I mean the story is that we prove it at tree level in bosonic string theory. So like a very sketchy outline of the talk would be in general like some motivation, evidence, and then the proof itself or the steps of the proof, which I divide in say strategy and then the actual details of each step. But since well, given the audience, I think we can skip or we can go very quickly over the motivation and the evidence, since everyone should probably be super familiar and expert on that, even more, well, certainly more than me. But okay, let's just dive in. So just to set the stage, weak gravity conjecture is the requirement of an effective field theory that can be completed to a quantum gravity to have super extremal particles, that is, charged particles, this side of the story, whose charge to mass ratio is larger than the charge to mass ratio of a large extremal black hole. And I mean, in the original story, and then for subsequent work, and we will use also something here. So the large means that we don't deal with the sub-Planckian problems, and also semi-classical approximation of the action for black holes uh, uh, will work fine. And so the main question here, okay, so before just to give a sketch of this stuff. So in various construction in string theory, there's been a lot of work on showing which like states appear as, I will say, towers of states, of lattices of states. Then we'll get to the refinements of the original weak gravity conjecture, mentioning all of those. But really, the hard question in general here is, it in any given theory, check or calculate what's the extremality bound. So what's the mass of an extremal black hole? Anyway, this is the story and where the complication lies. So the motivation, of course, this is something that should be very familiar with. Hopefully, this graph is somewhat intelligible. The idea is that we want black holes to decay, and in order to do so, if that was not the case, then black holes would form remnants of higher and higher charge and mass, and that will effectively be uh, 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 a parametrization, if you want, or a representation of a global symmetry. And since like we can take as a principle that quantum gravity doesn't have global symmetries, that requirement should imply the weak gravity conjecture. So this is the basic motivation, and then you say, okay, but really this is electric charges. So, but even for gauge group, if you consider a small coupling in the small coupling limit, and for large, this is also where the assumption of large black holes enters. This behaves like a global symmetry, so you will still have these remnants, and so you'd still have a problem from violating this condition on a quantum gravity. So that's the basic motivation. So this is a picture from the original 2006 paper. You want black holes, or in particular even extremal black holes, to be able to decay to particles that are super extremal, so whose charge is larger than their mass in the right units. Now, the evidence for it, also, this is something I think I can go over quickly, is in essentially in string examples, in particular toroidal toroidal compactifications. In these examples, you can write essentially everything. You can write the spectrum. This is the spectrum of your charge states. And you can also compute the extremality bound for black holes. That turns out to be like this. And so very easily well, this is okay. This is depending on the values of the charges, you satisfy the gravity conjecture. Maybe in some cases you saturate the condition. In some cases you have room to spare, like strictly super extremal cases. And then there are refinements of the original weak gravity conjectures, which say, in fact, something interesting about this, like if relating extremality and BPS-ness. So this is a sketch. This is also something that will be familiar. I'm only mentioning this because what we prove is actually a strict bound or a strict result. So I'll show you that we have states that are strictly super extremal in every string theory. Okay, good. So yeah, I'll need to go over all this. And so here, okay, so I guess the simplest heterotic cases with on a toroidal compactification, you have the spectrum that I showed before. There's a charge state for each Q in the charge lattice. And so this would imply something stronger than the weak gravity conjecture, that is the lattice weak gravity conjecture. That is, for each lattice side in the charge lattice, there is a super extremal particle. Turns out this is not true. This is violated, for instance, in orbifolds of toroidal compactifications. I think also this is probably also a well-known counterexample. But this I'm just sketching in the case where you have T3, T3 mod Z2, and then the Z2 is a symmetry between the first, I guess the N1 and N2, or the R1 and R2 are fixed to be the same by this Z2. So in this case, you can calculate what shows that the lattice is violated is this combination here, right? The mass of the charge states minus the extremal mass of a black hole, right? It's a function of this expression. And so it turns out that whenever N1 and N2 are different, this is positive. So this means that the would-be super extremal particles are more massive than the extremal black hole. And so that means that actually they are sub-extremal. So the case N1 different from N2 violates the WGC. But if you restrict yourself to the N1 equals N2 slice of the lattice, then slice, it's okay, whatever. Then you still satisfy the condition, and so then this is it turns out to be a sublattice of the original charge lattice, and so this goes under the name of sublattice weak gravity conjecture, which turns out is satisfied in all examples that we know. And so this requires that there is a finite index sublattice of the charge lattice for which at each site there you have a super extremal charge particle. And there's a similar related like story, which is the tower WGC, just mentioning for completeness, which is more or less the same thing, except the n is different from for each direction in the charge lattice, right? So the sublattice is stronger because it enforces a single n for which the I guess the sublattice of index n is filled with super extremal particles. Okay. And so this is here just to say that the sublattice, uh, as stated above, holds in all examples. Um, and we know, right, in general, we know the spectrum in terms of the charges in this in these examples, in these models. But in general, again, the mass of an extremal black hole is the question. And so okay, so then we know. And so we the goal of what we're trying to do is to set up a stage in a well, a different way, not work in a specific example, but do a more top-down approach from a worksheet string theory realization to show if and when we can satisfy the weak gravity conjecture bounds. So here, hopefully this is readable. So our strategy, it's mainly three steps. It's construct the tower of states that will be our candidate super extremal particles. Yeah, we're doing fine. And then we compute something of this from these charges. So we compute the self force. Now I haven't said anything yet about this. What does this mean? Let me just get to it. So self force is a statement related, well, in some cases related, or in some cases equivalent to the weak gravity conjecture, but it's a statement that that an identical pair of particles, or yeah, pair of identical particles should repel each other, right? So essentially, I mean, this is intuitively saying that it's the gravitational attraction cannot win against the electric repulsion, right? Plus, of course, if that were the case, if that was the only thing that entered in the picture, then that would be exactly the same as the weak gravity conjecture bounds. But in general, you have moduli, so you have to play with interactions of the moduli that can change the story. In particular, they change how they change the masses of these particles, right? And so they can change how the self force behaves. So we compute the self force, and why do we do that? Because then there is another step that I hopefully will get to that, and I'll show you, is that we can relate the RFC, so the repulsive force conjecture, which is read the weak gravity conjecture by replacing self-repulsive wherever you read super extremal, right? And so there's a way to connect this RFC and the WGC. In particular, let me just say it here, and then I'll repeat myself like 4 times. If a particle is self-repulsive everywhere in the moduli space, it turns out that means it is super extreme. So here, okay, so here I have just again like a statement of the repulsive force conjecture, which is this from 2016, Ben and friends, right? Again, something else that probably everyone is familiar with here. So the statement is that there is a state because it doesn't need to be a single particle state, a single particle, etc. It can be a complicated state that is self-repulsive. Okay, and so the self force, which is expressed in these terms, must be greater or equal than 0. In every of these conditions, the quality, or someone this saturates a bound, this is also a good solution for us, right? So for the RFC or for the WGC, those are good solutions. And here I have the expression of the coefficient, the script f, which is essentially tells you, right, the gauge or the electric field interaction between the charges, the mass, so the mass square here, this is the gravitational attraction, and this is the interaction with the moduli phi, right? So of course, for a single particle, this would be well, okay. If you diagonalize this is q squared, this is positive, this is negative, and this question mark. Okay. Oh, and then also here, in the WGC, there are refinements of the repulsive force conjecture. So there's the sublattice version, which is actually what we will show. So now, okay, maybe I should have not handwrite the slides. If you can't tell what I'm writing or what's written, like stop me and ask, because some things are not very clear even to me. So okay, so let me recap here. So we construct a tower of states, of charge states. Those will fill out a sublattice of our charge lattice. We compute the self-force between these charged particles, and this will be the bulk. I mean, this is, I guess, the bulk of our derivation. I guess what took the longest for sure. And then there's the connection between the RFC and the WGC, and showing that, well, let me just spoiler alert, since point 2 here will not depend, turns out that doesn't depend on the moduli, then the statement we find, so the self-repulsiveness of these states holds in general, which means holds everywhere in moduli space. So then this statement is true. So because we will have a repulsive, self-repulsive particle everywhere in moduli space, then that particle turns out to be super extreme. Right. So now, okay, so that's the strategy and the steps of the proof. So let me just stop for a second for questions, because then otherwise we'll dive into the details.
Hi. So are these particles that you consider, are they stable everywhere in the moduli space?
Yes. You could argue, you could ask at some point if there are. Yeah, the answer is yes. I think and they always exist. They always are. Part of the spectrum, and stable. There's something right in when the subtleties appear in point 3 when you try to connect the RSC and WGC. You could have problems if, I mean, there's some function that I'll define that I'll use to show this connection. If that function is not defined somewhere, which may be related to that, then that will create problems. But yeah, that's really more a question about the black hole solutions existing everywhere. That rather the spectrum, these particles exist and they are stable. They're fine.
Sorry, not understanding exactly why you're saying they are stable. There are examples of the ones which satisfy weak gravity are not stable for the full theory. Not the ones which violate, the ones which give you a -1 contribution, which are the more interesting checks of the weak gravity.
The non-BPS.
They are not stable anymore. So what do you mean?
I think he just means the moduli space that you see in the worksheet, like marginal.
Say again, I couldn't hear.
Okay. So Matteo, I thought you meant that when you said that we're talking about moduli space, you mean the moduli space that you can see perturbative portion, right? So the marginal deformations that you see of the 2D CFT, right? So not the dilaton, which is what
right. Well, the right. The dilaton, in fact, doesn't. It will not play with our other moduli. It just separates. So I guess you could say we don't see that contribution. Yes.
So you're saying perturbative is stable?
Yes. I think that's probably more a better statement. Yeah.
The heterotic ones are.
But sorry, but in the heterotic example you said, so how the fact that these I mean these are the states that satisfy the WGC, right? But so what is there an issue with the fact that they are not stable or not like exactly stable?
I thought that their lifetime was controlled by a power of GS string unit, so if GS going to zero, the lifetime become arbitrarily long.
Oh, I see. Okay,
So
so well, right, good. So in that case, then our states are exactly stable because we do everything at tree level, right? And so then we would not even see those issues, right?
yeah, I was just confused when you said that they're stable everywhere in the moduli space in terms of how you define the state everywhere in the moduli space if it's not stable. But now this makes sense. So you're focusing on
It's
part of the
the moduli
space.
space except the dilaton, except the string
Yeah.
correction.
So you're focusing in part of the moduli space where these states remain weakly coupled and infinitely stable.
Yeah, exactly.
Thank you.
Yep. Okay, so if if the steps of the strategy are clear, now we can get to I guess the meat, or for vegetarians the beans. I don't know. So the first step is to how we write like a way to write a general bosonic theory on the worksheet. And we use this approach essentially of writing the theory, the full theory here on the worksheet as a factorized factorized theory where we have this part I will call an external CFT that is taken to be say, a free boson in d dimensions. And then times an internal part, which is a unitary CFT with, well, we'll see, with conserved current and modular environment, all the right, good enough properties. And this is where the interesting things that then we can use and then compute stuff with enter, right? I mean, these are just free oscillators in each of the d directions, so this is just kind of boring. And
just to make sure your considerations do not apply to ADS, weak gravity and ADS, correct?
let's say again.
So your considerations do not apply to weak gravity conjecture on ADS, correct?
Correct. Yes. It's all flat backgrounds, tree levels. The mildest or the I guess most vanilla thing you could imagine. Yeah. Okay. So given this, I want to figure out which are my physical states. Okay, here I separated the massless sector and the massive. Physical states should be 1, primaries. And let me see how I wrote it here. Okay. Yeah, right. So these, well, this turns out to be, yeah, sorry. So these are the weights in terms of the internal CFT, right? The interesting, like tau int, or t int. And so we have essentially these types of massless states: 0, 0, 1, 0, 0, 1, and 1, 1. And the corresponding operators in the internal CFT, this is just the identity, and this maps to the graviton, the B fields, and the dilaton. These are conserved currents that will correspond to gauge bosons. And these, the 1, guys, are my moduli, or a portion of that will be the moduli that I care about. We'll see. I mean, there's some factorization here that I have to specify as well. And then in general, I have massive states with weight HH, and then the remaining part of the weight gets taken away by the external state momentum. But in general, I can just write for the internal weights, the spectrum in this form. And I guess it's the minimum of the left and right moving oscillators in the external part. So right. So now, with this writing of the theory, we can move to step 1. And step one is finding a tower of states, of these charge states that exist. Okay, okay. This is a story that's known, has been known for a while. And essentially, let me just first, well, okay. I think I'll just I'll get to the result and then I'll trace back and say how you get it. So the partition function in general is written in this forms in terms of, well, you can write it as a sum over the spectrum, right, like this, where H and H tilde, right, good. And then to calculate, sorry, to see essentially the charge in these in the partition function, you can introduce the flavor partition function, which is no longer a modular invariant, but it takes this form, right? You introduce these fugacities or chemical potentials that keep track of the charge of the states. No, and I wrote it here. It's no longer modular invariant, but the transformation of this object are known. Were found in a paper in 2016, I think. And so this this is just the expression, and this is what then you use, you apply to imply something about the spectrum, the spectrum of states. Okay. So okay, here first new result. I don't know, this doesn't it's not highlighted well, but first thing, well, we found that, well, actually it was the last thing we did, but anyway, it appears as the first. There's a so the derivation of this expression or this transformation is a little murky, at least in my mind. It's in some appendix of a paper in 2016, but it's not very clear how and why it works, because they do something at first order expansion and second order, and then say, and then imply that this is obvious and this is the full result.
Sorry, I have a question. I recall this kind of thing with the K in the denominator somewhere. Where's your K, the level?
Oh, probably
You scored over 2K, I remember vaguely. Am I wrong?
I don't think in these expressions there's a K.
Are you assuming level is 1 for the current?
Or we yeah, okay, so in the expressions I remember, I don't recall a K, but either way, I think we are assuming it to be 1.
Well, I think there is a K in general, and you can get this formula by writing the current algebra in terms of the free boson and parafermions, the usual description, and then you get this formula just from the free boson part for the carton. So
I see.
Famous one, and there's a K, so I think you're not correct.
Okay, I see. Oh, I see. No, you're absolutely right. Yes, because sorry. So the stuff that I'm about to say, actually, it depends on the JJOPEs, and so there you have a K. It's fixed to be 1. Yeah, you're right. Right, good. So what I just want to say that you can get this result. Maybe this is actually exactly what you were saying. You can get this result by just figuring out what Z with insertions of some appropriate operators is, and this boils down to be the difference between two different normal orderings of the current. The JJ current I guess OPEs. One is this, which is not the usual one. We call it modular normal ordering, and this is in cylindrical quantization. So this is essentially requiring that you always have an analytic function. So as W1 goes to W2, or maybe I wrote as W goes to 0. Anyway, as the difference goes to 0, you don't get singularities. So this is a prescription to do that. And then you can compare with this guy.
Can you ask what is the P? Oh, you're saying, right? Okay.
Say again?
Okay. The P is just some more.
P is the Weierstrass function. Yeah. And so here I just have the usual one is this, which is P plus a piece. Essentially, everything boils down to the fact that this guy, the E2, is not modular invariant, right? Sorry, it's not it's what is it? Quasi-modular. What do you call it? Quasi-modular, I think. So the failure in the Z with chemical potential being modular is just dependent on this guy. And so right, so this is what we want to compute, Z as with this insertion, but we can relate it to this other guy, which we have constructed to be analytic, and the difference, that depends on proportional to E2 is what you get. And so I mean, okay, this is just very brief. I don't think I'm saying anything more useful or more like new. This is just the known result, but this is just a neat way to construct it. Now, the interesting question is how to apply this result. And so here you have this equivalent invariance under a shift here, which is in the dual of the charge lattice, right? Because mu dot q is an integer, so the mu, and so therefore rho must be in the dual of the charge lattice. And so you can use this to re-express your z of mu tau in this form, where you essentially factor out two pieces, one that depends on the charges, and one the h hat that is the remaining part of the weight. And then because of this invariance under the mu going to mu plus tau, you get this invariance of the spectrum. So so this essentially is saying if there is you have a state of charges q tilde, then you also have to have this guy, right? And so then what we actually do is you start from a charge with a state with charges 0, 0, like graviton, and then the rows have to be the shift, right? The row factors have to be of this form. So this implies that states with any charge, a half q square, a half q tilde square, exists in the spectrum because the graviton exists. And in fact, this is what I have here. We have a spectrum of, this is in the usual jargon is the spectrum of charge states related by spectral flow to the graviton is of this form. And well, these are the lightest states for each charge, right? Because then otherwise you could have, this is just for the internal bit, and then you could always add oscillators that raise this by integers, right? So this implies that you have a sublattice of charge states in every string theory. Again, this is all tree level and so on, but in every string theory, because there is a graviton, you have these charge states. Okay, that's step one. Now, I think I have to go faster. Step two is the computation of the self force, and now I have to trace back to, okay, think about the EFT. What do you have in the EFT? You have a charge, essentially Maxwell coupled to gravity. So you want to, I forgot to put them, these are psi's, supposed to be psi's, your charge states. And they're force mediated here by, for instance, gauge bosons, but it does not mean the interesting bit here can be gravitons, gauge bosons, and moduli. So in fact, this expression or the self force, right, between the charge states depends on these guys. The interaction with the gauge bosons, with the photons, let's say, interaction with the graviton and with the moduli. And then there are additional bits that essentially are used as normalization. These guys. Let me just gloss over those. But these are yeah, okay. These are just normalization factors at the end of the day. So the interesting story happens here, actually. Right, good. And then so here you see I wrote the three pieces like that just to highlight again the self force splits in these three terms. And here these are the combinations without the normalization factors that these depend on, as charge state, photon, then the propagator of the photon, and the photon again on the right side of the diagram with the charge states, and so on for the other two interactions, right? Gravitons and moduli. Okay, so now, now the interesting story about, well, interesting story. The advantage of writing everything the worksheet like this is that turns out that these three-point functions also factorize into pieces that only depend on the external bit. That's a free theory, so we know everything about it. We can compute it. Well, these are universal properties. You can compute them once in an example, and then you're done. And then these are the remaining interesting bits. So the correlation, the three-point functions that come from here. Okay. Right. So now, now here I'll go super fast over this. This is sorry, when I wrote F graph before, the dilaton actually enters in this story because the dilaton here, that's phi 0, that's a modulus from the original story, but from above, but doesn't talk to the this is related to the questions from above, doesn't talk to the other moduli, the phi I, because in terms of the internal CFT, G and phi 0 are the identity. So this is just a one-point function of something that's not the identity, so that's 0. So there's no mixing here. So that means that the F the self force here of the gravitational part and the dilaton is just fixed. It's in a universal way. So it only depends on the external part, the external free part. Similar story happens in the gauge sector. Well, except here you have something non-trivial in the internal bit, but these are conserved currents, so you know exactly there are these two-point functions, right? Just up some normalization. These are fixed like this. And then the interesting bit here, I remember there's these terms, psi j, but these, because of these expression, I guess the OPEs here and the modes of the current can also be written immediately because because we know J, and like the integral of J here gives you the zero mode J0, which gives the charge of the states, and the charge of the states was derived from above. From point 1, we derive which the charges of these states, and so we also have F gauge to be fixed. Well, here it's fixed up to these it's called the normalization factor, but these again are universal quantities. So this is the expression for that part of the force, the self force. Well, force here, I do not set them equal yet. And then let's get to the interesting bit. The interesting bit is the interaction here with the moduli. And remember, these phi I came in as 1,1 primaries of the internal CFT. And so you have to ask what do I have here? What options do I have, right? So the interesting bits are these moduli, but then there's some remaining bit, the remaining part, which is this combination of the currents, which is also 1,1 primary. So you want to make sure you treat these guys separately. So you ask, well, first you compute this. And this is also known by the argument above because the currents are known. You have the zero modes of the currents on the charge state, so you know exactly what this is. And then you have to compute the other bit. But first, you have to require this. Right? Otherwise, you would have mixing, and then that's not a diagonal thing. So you wouldn't know what to do between the two. This you know, but then this is what we care about. But why is this? We can requiring this is equivalent to this. So did I forget a? Sorry, there's a one here as well, right? Okay. And right. So then asking that you have a neutral current primary, so this is zero, then implies automatically no mixing here. So then neutral primary means that you can do this, and then okay, then you don't have a mixing between those two 1, 1 guys. So then the only thing remaining to be computed is this 3-point function. But then I can give the brief. Yeah, I think I'll give the brief argument, and then maybe after, if someone is interested, I'll go in more detail. But the quick and dirty way to do this, to show this, is to exploit the Sugawara construction or the composition of your theory. So you write the the stress tensor in terms of a current part, and an orthogonal part. And this, you know exactly what it is. It's written in terms of these currents. And all the magic now happens because you know the charges of these charge states, the psi's, and you're using neutral moduli here. Well, I mean, the modulus is a scalar, neutral scalar, but so you're using these facts here. So these are the charges under the composed internal theory, the current part and the orthogonal part. And so the magic is this: is that on one side, chi has weight 0. On the other side, the size, the charge states have weight 0. So what essentially happens, I mean, you can show it in more detail, but what essentially happens is that this 3-point function factorizes into the 2-point function of the current part times a 1-point function of the t hat part. And so again, because this is not the identity, this is 0, identity, right? This is by construction is 0. And so this is where all the magic happens and what allows us to do the rest. So this 3-point function, the last remaining bit that would have been the non-universal bit parameterizing the interaction between these charge states and this modulus or moduli in general is actually vanishing. So I have another argument here, but I will skip it. You can, I mean, it's neat though. You can. Well, I spent a lot of time doing it, writing the modes and expanding the modes and making sure that the modes behave in the right way. There's a neater way to do it. It's just applying some contour integration and so on. But I will skip this because the result is this. And so then you can compute the self force. Remember for the phi I contribution, remember there was the lambda AB contribution. So that's really the only thing that you're computing here. That in fact, you get this charge dependence. And so now you have all the pieces. You can compute the self force. Turns out to be this pretty expression. And so the question is, okay, now remember from the strategy, I want to ask, when does this provide a self-repulsive particle? So when is this force greater or equal than 0? And this happens in these ranges, depending on which of the Q's is larger. But the interesting bit, and let's see if I have it. Yes, here. Let's do this. It's probably easier to read. Yeah. So the interesting bit is that no matter what the charges are, the n = 1 states are always self-repulsive. I mean, really, they have zero self-force, but they always satisfy the repulsive force condition. So you have these states that always exist by point 1 of the strategy. They always are self-repulsive. So now the last bit is to ask how to connect this to the super extremality bound, right? So all right. So at this stage, right, just because these states exist, and I've shown this for general Q in this tower of states that exist, this is just showing that the sublattice RFC is satisfied. So now the last bit, which I think also I'm running out of time, but let's do this quickly, is to connect the self-repulsiveness and super extremality. And this is an argument that, well, actually Ben came up with himself. I think he wrote it in another paper and then ended up being in our paper because I don't know if he published the other one or not, but I'll just give a sketch of the proof. This is just a refined. I need this to say the following. Just the refined statement on the WGC is that you have that the charge to mass ratio is bound by these. Sorry, let's see. How do I want to say? A particle is super extremal if its mass is not larger than this combination, right? Where in the limit for in this combination for an extremal black hole of this charge. So this is where these ends are the same, of course. In the limit as n goes to infinity. And I mean, in the end, this in the super extremality bound just boils down to the fact that you can remove these ends. But this is strictly true, or this WGC is strictly true in this large n limit. Just to avoid, again, problems with small black holes and sub-Planckian scales and so on. But this is actually fundamental in the next page. So the way to show this connection between RFC and WGC, or repulsiveness and extremality, is take a black hole solution with good enough property, like spherically symmetric, and yeah, I think that's it. Charge spherically symmetric solution like this. These are the solutions. It turns out that you can write an expression for its mass here. That is a functional of the I guess the psi and phi in the moduli. But really, what happens here is that you introduce this m, and this is something that I mentioned before in some of the questions. That this is a function of phi. That but this is true if this m is well enough behaved, so that means that it should exist in moduli space. So if this is true, then you have that the mass of the black hole is bounded from from below, and so the mass of the black hole is larger than, let's say, that this quantity, provided that star is never negative, right? If this is a if this is a non-negative quantity, the exponential is, then mass of the black hole is bounded by this guy. So now what's the magic? This expression, okay, this is for a charged black hole of charges Q, QA, QB, and then M is an arbitrary function of the moduli. But then take star and do the following. So right, this is the statement. But so take star. Star looks very much like the self-force of a charged particle that we had just computed in point 2, which is here, right? So the only difference is this. Well, the charge of the black hole was the large Q. This is small q, and then these are the little m's. That was a large m. But with this refined notion of the refined statement of WGC, like being valid at this large n, this is exactly what allows you to say that that the WGC satisfy. Why is that? Because I pick my n equals 1 states from from 1 that exists from point 1, and from point 2 I show that their self force is 0. So this expression is 0 for my n equals 1 charge states. And then I essentially what I multiply by n squared here, right? So then this becomes large Q, which is large N times little q, and then this becomes large M, which is large N times little m, like this, right? And then the other bit that I'm using is that this doesn't really change, right? Because this is 0. So it's not, there's no dependence on the moduli, really, right? Because remember the interactions, the last bit interaction with the moduli doesn't, it vanished. So this just allows to say, to put a bound on the mass of a black hole, which then you flip it around, you write in the right limit, and you put in the ends and so on. It happens to be exactly the weak gravity conjecture statement, right? So you've showed that these self force equals 0 particles actually satisfy, in fact, well, they saturate this. But then what's a beautiful thing, that in addition we can say that these are the n equals 1 states. So these can saturate this bound. There can be yeah, there are what is it, more massive black holes, but at least you saturate the bound. But there are lighter states, right? Because in these towers, there's also always the n equals 0 states. And so those, turns out, I mean, this is again the related to a question from above. This is bosonic string theory, so we don't have BPSness and so on, but the n equals 0 states are the ones that are strictly super extremal. So they satisfy the weak gravity conjecture with room to spare, and room to spare is by 1, which is really the scales are alpha prime, right? It's an alpha prime, this difference between this and this. And so what we've shown is with these 3 steps, okay, with the right caveats, bosonic string theory, flat background, 0 cosmological constant, oh yeah, that's the same thing, 3-level spectrum and so on, but we've shown that states filling out a sublattice of the charge lattice exist. These states have 0 self-force, and because of this, they and because the self-force also does not depend on the moduli, these are super extremal. And in addition, there's always strictly super extremal states as well. So right, this is a summary, and right, I just recapped what I said here. And so again, just to reemphasize, we showed the sublattice RFC, and that, because of the last argument I just gave briefly, that implied the sublattice WGC as well. This is the main thing that we calculate to make sure that this is possible, and this is the general final result at tree level in bosonic string theory. This is true, and yeah, with some caveats. So yes, good.